Okay, so we're going to finish up section 4.2, which is on more graphing. Okay, so the kind of graphs we did yesterday fit this description. All of the graphs, either the numerator was less than or equal to the degree of the denominator. Right? So basically that would leave you with end behavior models that were something like this. Let's say 3x cubed divided by 4x to the fourth. What would the end behavior model be there? Let's say these were the leading terms. Just simplify it down. Yep.
3 over 4x.
Yeah. And this fraction would approach what?
0.
0. Right? So you could have horizontal asymptotes at 0, if this is your case. Or what if you had something like 3 over 4, then you had x squared and x squared?
3/4.
Yeah, that reduces to 3/4. Okay, you still get a horizontal asymptote, but now it's not at 0, it's at 3/4. Those are the only kind of horizontal asymptotes we had yesterday. And those are the only kind you can ever have. Right. What we're going to look at today is what happens when the degree of the numerator is bigger than the denominator. So we're not going to get cases like this, but we'll see what happens. It's going to change our asymptotes a little bit. Not so much the vertical ones. Those are going to stay the same. But we might see the horizontal ones going away.
This is yesterday's lesson online already?
Yes.
Okay.
Okay, so any question about what we're going to do today? All right. So first thing that we need to know how to find, which is going to help us with the new types of asymptotes we're going to get, it's called the EBA, or End Behavior Asymptote. Okay, the End Behavior Asymptote is only something you find when the degree of the numerator is greater than the degree of the denominator. It's not something you would use for any of the problems we did yesterday. Right, so suppose we had two polynomials, h of x and g of x, as a rational function. And if we divide these two things out using long division, we're going to get a quotient and a remainder. It's possible the remainder could be 0. It could go in evenly. Maybe not. Doesn't really matter. But the point is, when you divide these, you're going to get a quotient and you're going to get a remainder. Okay, q of x is my quotient. R of x is my remainder. And usually when we do long division, we write our final answer as quotient plus remainder over my original denominator. Right? That's how you write your answer. Quotient plus remainder divided by my original denominator. Well, the end behavior asymptote is just the quotient. That's it. So we're not doing anything we haven't done before. You're going to do out long division, but you can stop once you have the quotient. You don't need to find the remainder. All right, so this is what your end behavior asymptote is. It's the quotient when you do long division. Any questions what the end behavior asymptote is?
Can you keep it there so I can copy it?
Mm-hmm. Right, so the first one we'll do, we're not going to sketch it right away. Let's just try finding the quotient, the remainder, and then the end behavior asymptote, which is really just the quotient. So it's 2x cubed minus 4x squared plus 3 divided by x minus 2. Could I use synthetic division on this one?
Yes.
Yeah, it's a linear factor in the bottom, x minus a number. Okay, so put the number after the minus sign on the outside. What would be my numbers that I'd use for synthetic division? And be careful here, Graham.
2, -4, 0, 3.
Yep. 2, -4, 0, x, and 3. All right, we'll divide it out. This time they actually want the remainder, so they're asking for it in addition to the end behavior asymptote. So we do have to find it this time. So we got 2 2 times 2 is 4. Add them, we get 0. 2 times 0. Add, we get 0. Okay, 2 times 0. Let's see, we get 2. And my remainder is 5.
Wait, how did you get 2 times 0?
Minus 3.
Oh.
Minus 3.
Thank you. Yeah.
Yeah, that can't-
Yeah, it just. So we brought down our 2. 2 times 2 is 4. Negative 4 plus 4 is 0. 2 times 0 is 0. Add them up, we get 0. 2 times 0 is 0. Add them up, get 3. Thank you.
Oh,
All right.
I think you were thinking like ahead of yourself a little bit.
Yeah.
Just 2's in the next.
All right, so now we got to focus on this 2. Okay, that's my quotient. Okay, so what's my quotient?
2x squared.
2x squared.
With the plus 3 over x minus 2.
That's not part of the question.
Okay, yeah, we can do it that way first then. So the final answer is 2x squared plus 3 over x minus 2. Okay, now I'll just circle it. That's my quotient. That's my remainder. Okay, and my quotient is also my end behavior asymptote. Okay, so we can write it that way, that's fine. Okay, now, what happens to my remainder as x gets really big? What does this remainder approach? It approaches 0. Okay, again, pretend x is 1,000,000. If you took 1,000,000 minus 2, 999,998. If you take 3 and divide by what I just said, that's extremely small. Okay? And as x gets even bigger, this fraction gets even smaller and smaller. So the remainder approaches 0. That's why when we're finding the end behavior asymptote, the remainder doesn't really matter because it just gets so small. It doesn't even make a difference. Okay, so any question on that? So we can say remainder approaches 0. It gets very, very small. Does everybody have what's on the left? So I can make the right a little bigger. All right, so 3 important points. Okay, there's a difference between an end behavior model and an end behavior asymptote. End behavior model, that's easier to find. Okay, if you've got a fraction, you just take the highest degree term in the top, divide by the highest degree term in the bottom. Okay, this is what we did yesterday. End behavior asymptote, that's what we're doing today. You have to use long division or synthetic division, and then write the quotient. All right, so end behavior asymptote, end behavior model, a little different. Only use end behavior asymptote when the degree of the numerator is bigger than the denominator. Sometimes the end behavior model and end behavior asymptote are the same. Sometimes they're different. Depends on the problem. Okay, make sure you know the difference in how you find each one. Okay, if we have the kind of problems like we did yesterday, where the degree of the numerator was smaller or equal to the denominator, we had straight line asymptotes, whether they were vertical or horizontal. Okay. Sometimes they were horizontal at 0. That usually happens when you had a fraction and there was a variable left in the bottom. Sometimes the variables canceled out and we had a horizontal asymptote at a number other than 0. But if the degree of the numerator is not less than or equal to the denominator, we can end up with curved asymptotes. Okay, we won't always have asymptotes that are straight. So an example of a curved asymptote would be if you had something like, say, a parabola, and maybe you have some kind of function that let's just make this dotted. So there's my asymptote. And maybe I have a function that does something like this. Right, this side of it just gets closer and closer and closer to the asymptote. Right? So it's getting closer and closer to that curve. Okay, any question on that idea? Right, we're going to do one in a second that's a curved asymptote. I'd never give you an asymptote any more complicated than a parabola. So degree 2 is as high as we would go. But in theory, the degree could be as high as you want. But that would get really confusing.
What happened to the other side of that curve?
On this one I just had kind of dropping off.
Oh, but the line split off to go the other side of the curve?
You could have a second part to it. You'll see today that we will. Yep. You could have a second part that kind of maybe comes in, on this other side and gets closer and closer. It depends on how the graph is set up. But yes, in general, it'll get closer and closer on each side. Yeah. All right, so let me show you that. Okay, I'll graph the end behavior asymptote we just found, and let me graph example 5. All right, so I'll try to do the asymptote as a dotted line. 2x squared. Okay, and let's make that dotted. So there's my asymptote. And now I need the original problem. All right, original problem was 2x cubed minus 4x squared plus 3. Squared plus 3. Again, make sure you're putting parentheses around numerator and denominator. X minus 2. And do zoom 6. There's our asymptote. Okay, this one I can see it on the left side. Does everyone see how that red line is just getting closer and closer? I can't see it on the right, probably because it's up above. So let's set our y max. Set it to like 30. Right, so there's the left side getting very close. And there's the right side. Okay. What's happening at 2? What's happening right in there? Yeah, we have a vertical asymptote. All right, so this one has a vertical asymptote at 2. And then it's got this other asymptote in blue. It's a parabolic asymptote. Right, so for this example, all they wanted you to do was sketch that and look to see, does it look like the red line is getting closer and closer to the blue? And it is. Okay. Any questions on that? All right, so now let's try to sketch that by hand. Okay, it's got 2 asymptotes. And the first thing I would do is sketch the parabola. Okay, that's the asymptote. I'll do it solid, but then I'll make it dotted. Okay, to sketch that, just pick some values for x and then find the y's. And 0 would be good. Let's try 2, 3. And then let's do -2 and -3. If I plug 0 in for x, what do I get for y? 0. How about if I plug in 2? 8. And while we're doing this, what about -2?
8.
It's also 8. 3? 18 and -3? -18. All right, so that's probably enough points to sketch it. 0, if you want to throw in 1, you could. When you're at 1, y is 2. Keep in mind, my y-axis, I went by 2's because I didn't have enough space to get all the way to 18. All right, 2, we're at 8. -2, we're at 8. and then 3, 18, negative 18. So I'm going to try to sketch that asymptote. Okay. And because it is an asymptote, let's make it dotted. Okay. Any questions on that? All right. Now, where is my other asymptote? I have one other one.
2.
Yep, at 2. Oops, I don't want to do that. All right, so there's my other asymptote. So we've got a couple sections here. We're going to look at what's happening. Let's make this bigger. All right. Now, I'm going to check the behavior on each side of that asymptote. What's a value that's just a little bit smaller than 2?
1.99.
Yeah, that's good. Okay, we're not at 1.99. We're way down at negative 300. Close enough. Okay, and then we're going to check what happens just after 2. Okay, what's a number that's just after 2?
2.001.
Okay, and now we're up at 300. All right. So we already saw that it's going to hug this kind of left-hand side, get closer and closer to it. So we have to connect this dot to this dot. Right? And it's got to be curved, and it's going to get closer and closer to both of those dotted lines. So maybe something like that. Right? So as we continue on each direction, the gap between the dotted line and the red line is getting smaller. All right. Now in this part, we know that we're going to get closer and closer to this dotted line in black and green. So the only way that can happen is this is going to kind of come down. At some point, it's going to turn and then go back up. Where exactly it turns, that I'm not going to be overly picky about because it's such a small area you're trying to sketch. It's hard to be precise. That's our sketch. Let's compare it to what we had. Looks pretty good. Not sure if I crossed the y-axis at exactly the right point, but that's okay. It also looks like maybe it curves up a little bit more before going down. That's fine. It's the basic idea. Any question on that? So now if you just wanted to see the final picture, you could take both your asymptotes out, and now you could see that's what the graph actually looks like. Okay, just what's in red. Okay, I usually leave the asymptotes because it's too difficult to try to erase them without messing up the rest of your picture. All right. Now look at the leading term in the top and the bottom. What's the degree of the term in the top? And what's the degree of the one in the bottom? How many degrees off are they? 3 and 1. 2. We had a degree 2. Okay. Notice that's what the asymptote was. It was second degree, parabola. Okay. What's the degree in the top here? 3. In the bottom? 2. How many degrees are they off now? 1 degree. So this one's going to still have a different kind of asymptote we haven't seen, but it's not as complicated as a parabola. Right? It's going to be a degree 1. All right. So let's find the end behavior asymptote first. Right. Can we use synthetic division this time?
No.
No, it's not x minus a number. Okay, so we do have to use long division. X squared plus 2x minus 3. 2x cubed, 7x squared minus 4. Tom, what's 2x cubed divided by x squared?
2x.
Good, 2x. Okay, multiply it back out. I get 2x cubed. One thing I should do before I keep going fill in a 0 for my x term, just like we would with synthetic, so we don't lose our place. So I get 2x cubed, 4x squared, minus 6x. And subtract. 2x cubed minus 2x cubed is gone. Heaven, what's 7x squared minus 4x squared? Okay, you get 3x squared. And Olivia, 0 minus 6x.
Plus 6x.
Good. Okay, bring down on 4. And now we've got 3x squared divided by x squared. What's 3x squared divided by x squared? 3. Now I'm finding the end behavior asymptote. Do I need to keep going?
No,
No, I don't. Why not?
because you don't need the remainder, you already have the quotient.
Yeah, there's my quotient. If I want the remainder, then I'd have to keep going. Okay? But if I don't need it, just stop. Okay, so my end behavior asymptote, it's not a parabola this time. It's 2x plus 3. What is that?
That's a linear function.
It's a line. What kind of line?
A line that has a slope of 2 that crosses the y-intercept at positive 3.
Yeah, so it's not horizontal or vertical, right? It's got a slope of 2. So it's slanted. And we call this a slant asymptote. Right? So this asymptote is going to be on a diagonal. Not as complicated as a parabola, but not as simple as just being horizontal. Right? It's a slant asymptote. Right? So I'm going to graph that. Okay, just really quick, how do we graph a line? What do I do first? Yep.
Start at 0, 3, for your y-intercept.
Right, there's my y-intercept.
Up 2, over 1.
Yeah. Go up 2 and right 1.
And down 2 and left 1.
Yeah, you could also go the other way too. Okay, so drawing your line, maybe about like that. And now what's going to happen as we get towards the end of the function, it's going to get closer and closer to the green line. Okay, remember, the green line is just for the end behavior. It doesn't describe what's happening near the origin. It says we get far away from the y-axis. All right. What else should I find besides my end behavior asymptote?
The horizontal asymptote.
Well, this is taking the place of that.
Oh, okay.
The EBA takes the place of a horizontal. But there is another kind of asymptote.
A vertical asymptote.
Yeah, let's find the vertical asymptotes. Vertical asymptotes are when the denominator equals what?
0.
So x squared plus 2x minus 3. Yep, if it doesn't factor, use quadratic formula, but that factors. We're going to need a plus and a minus.
Plus 3 minus.
Let's check. We get minus x squared plus 3 minus 1 plus 3 is plus 2. Yep, so that's good. Okay, where are my vertical asymptotes?
X equals -3. X equals 1.
Right.
So let's
Now, normally we have to check the numerator and make sure that these are not factors, because if they are, these wouldn't be asymptotes. They would be
whole.
wholes. But a cubic is very hard to factor by hand and in general, and I wouldn't be that tricky. All right, so let's just go with the fact that these are asymptotes, -3 and 1. Oops. So -3 and 1. All right, so now our graph, it's kind of broken up into different sections. Okay, so we're going to see what sections our graph could be in. It's basically 6 sections here. Okay, we've got these 2 on the left, 2 in the middle, and then 2 on the right. All right, so now check the behavior on each side of the vertical asymptotes. All right, so now we got to type it in. All right, and we've got 2x cubed, 7x squared minus 4. So 2x cubed, 7x squared minus 4. Divide by x squared plus 2x minus 3. X squared, 2x minus 3. All right, if we got everything correct,
Yeah.
I think we're good. Okay, there's negative 3. Maddie, what's a good value that's just to the left of negative 3? Just barely. Negative 3.9? That's probably a little too far, because that's closer to negative 4. I want to go just barely to the left of negative 3.
3.1, negative.
Yeah, I would even do even closer. Try to stick within 1/100th of that asymptote. All right, way up at 121. Okay, Steph, what's a good value that's just barely to the right?
2.99.
Yeah, close, not 2.99, but that would be over, somewhere over here.
Negative 2.99.
Yeah, negative 2.99. Okay, and in that case, I'm approaching negative infinity. Okay. Way down there. All right, now my other asymptote. Brad, what's a good value to check for this other one?
0.99.
Yep, that's a good one. In that case, we're way down, negative 100. And how about Corey, what's another good value to check?
1.00.
Good. In that time, we're up over 1,200. Okay, so now we're up here. Now keep in mind, you're not going to cross any of these dotted lines. So in this left-hand section, I can't cross this vertical line and I can't cross this line coming down. So my graph is going to have to come down, it's going to curve, and it's going to hug that asymptote. Right, so that part's going to do something like this. Okay, on the right-hand side, I can't get out of this little section. So I've got to connect those two dots, and it's going to take some kind of sharp turn like that. Okay, now in the middle, we've got these two dots, and they've got to be connected. You can't just connect them with a straight line. What do you think would be helpful to give us a little more information in this middle area? Yeah, let x be 0. See what we got. Okay, when x is 0, we're at 1.3. I would even do maybe like negative 1. See where we're at there. Negative 0.25. Right, and I think that's enough information. So we're going to have to get close to all three of these asymptotes. So this one is going to do something like that. That one does something like that. And then that. And we need to connect all that. So it's going to come something like that. So there's our graph in 3 pieces. Let's see how we did. Let's take it off of dot mode. That's not very helpful. Let's put it. Yeah, let's put it like that. Okay, so there's that left-hand side. Okay, there's the piece in the middle, and there's that top piece. We're cutting it off. We probably have more like a standard window, so we can't see the whole thing. That's kind of what ours looks like. Right. Any question on that one? All right, and okay, anybody want to try another one of the sketches? This one's only going to have, well, how many vertical asymptotes here? Just one. So this one's going to be, it's going to be a little simpler. It's going to have a vertical asymptote. It's going to have a slant asymptote. And that's it. So you've got 4 sections. Could be something like this. Right? Could be in the other 2 sections. Depends on the graph. But anybody want me to go through this one? So it'd be okay if you had something like that on the test?
You should just do it.
Do it? All right. So let's find the vertical asymptote. -2. Throw that in. Find your slant asymptote. Since that's a degree 2, that's a degree 1. I know it's a slant asymptote. Actually, you know what? Synthetic division. Let's just use that here. What number goes on the outside? -2. Numbers on the inside?
1, -2,
Positive 0. Bring down my 1. Gives me -2. -4. Really, I can stop. That's my quotient. So let's just stop. What's my end behavior asymptote?
X minus 4.
X minus 4. So slope of 1, y-intercept at -4. Draw that in. Now just figure out what sections you're in. Okay. All you got to do is check the vertical asymptote, check to the left and the right, and that's going to tell you everything. All right, so let's type it in. X squared minus 2x plus 3. X squared minus 2x plus 3. And divide by x plus 2. Okay, what are the 2 values I should check here for my asymptote? -2.001. So when we do that, I would say we're at -infinity. And what's one other good value?
-1.
Yeah. Since I already know I'm down at -infinity on the left, I'm going to be at positive infinity on the right. Okay, up over 1,000. All right, so this one is going to be trapped in this upper section. So it's going to come down. At some point, it's going to turn, come back up. And this one is also going to be trapped in this bottom section. So it's going to come up, take a turn, come back. Let's see how we did. Okay, now here, this graph, it's possible the turn is actually happening off the screen. So just set your y min. We should definitely see it by -20. Yep. There it is. All right. Any question on that? Okay, and mine looks a little different, I think, just because of the window. But if we wanted to double check that we had the right asymptote, just type it in. What was it? X plus 1? Was that our end behavior asymptote? It was.
No, it's X minus 1.
Oh, X. Okay, I was going to say, I hope it's not X plus 1. X minus 1. right? And it should look like it's right in between them.
Yeah, I thought it's 4.
What?
It's x minus 1?
Yeah, it's not 4. Oh, it's X minus
No, x minus 4. Thank you.
We're way off. Hey, you thought it was X plus 1.
A lot of numbers today.
Yeah, that looks better.
Yeah, that looks good. So it's going to get closer and closer. So, yep, our graph is perfect. Okay, just the window distorts the picture a little. All right. This one, I don't want you to find anything by hand. All I want you to do is graph it. Okay, and I want to show you something interesting, something to be careful of. Okay, that could happen. All right, so in the top, you've got 2x to the 4th plus 7x cubed plus 7x squared plus 2x. Okay, and in the bottom, x cubed minus x plus 50. So we'll try a standard window. Actually, no, I'm just going to leave my window the way it is. I'm just going to try that window. See if it works. Okay, there's my graph. Is there anything about that graph that we might want to look at a little closer? Yep.
I feel like I take it.
Yeah, there's this flat part, okay, right in here. On that window, it looks very flat. What do I have to change on my window to kind of zoom in on that section? Yeah. Change the y's. Instead of negative 10 to 10, let's try negative 1 to 1. If that's not enough, we'll do a little more. Oh, I changed the x's, didn't
Yeah, I
I?
was going to say.
Leave that at negative 10 to 10.
It actually goes under. Goes below.
You can't do
Like a little bit.
All right, so it's still, yeah, it kind of looks like it comes down a little. It's still kind of hard to see.
Negative 3 to 1.
Let's go negative, yeah, let's go 0.1.
Oh,
So 0.1.
that's 2 points.
Now look at it. So was it really flat?
Well, that's weird.
I don't like that.
No. In fact, it crosses the x-axis how many times?
3, 4.
4. All right.
What?
So something that originally looked kind of flat, okay, when we zoom in on just that section, actually crosses the x-axis 4 times. So my point is just be careful when you graph something that you zoom in and look at it carefully. I would not have you sketch something like that. But I might ask you how many intercepts it has. And if you look at that, you may say, it doesn't look like it has any. But zoom in and look at it a little closer.
So if we were to like graph that, we would just do a straight line. Can't really see it.
Yeah, if you were just graphing this by hand, all you could really do is use a straight line. All right? But again, I'm not going to give you something that complicated to graph. Just purely something I want you to be careful with on the calculator. All right, and let's take a look at our last problem. Okay, so we've done problems like this before. Okay, rectangles with certain perimeters or areas. All right, so in this problem, I want you to consider all the different rectangles that have an area of 200. Right, so that could be 10 by 20, could be 2 by 100, okay, all of them. All the different rectangles that have area of 200. I want to find an equation that represents the perimeter as a function of x, where x is the width of the rectangle. Okay, and once I do that, then I want to find the dimensions of the rectangle that have the smallest perimeter. Right? So I want to enclose the most amount of area, and I want to do it with the least amount of material. Right, so let's see what happens. First thing, let's make a sketch. Area is 200. Okay, what about the width? How did they say to represent that?
X.
X and X. Now I want to represent the length. Okay, but don't use a different letter. You know the area and you know the width. You can find the length.
200 minus X, 2X.
Divided by X.
Oh, yeah, that makes more sense.
Yeah. If you're not sure how Matthias got that, well, you can kind of look at it backwards and say, all right, take this times that, you get 200. Or, here's your formula for area. Length times width. Our area is 200. We don't know the length. The width is x. Solve for length. Your length is 200 divided by x. Okay, and now what is the perimeter
The perimeter
of that rectangle? 2x.
2X plus.
So we got this. We got that.
400 over x squared. Can you do that? No.
No.
So when you add fractions, what do you do with your
400 over
X.
X.
over x?
Yeah.
Oh, and just do 4s then.
Yeah, when you add fractions, keep your denominator the same and just add the numerators. Okay?
I don't
So-
know why it times them.
So you got your quotient and your remainder.
Okay.
Okay, so here's your function for the perimeter as a function of x. Okay, now we're going to graph it, and we're looking for a smallest perimeter. So let's just graph it and see what it looks like. Got 2x plus 400 over x. I would probably put parentheses around that.
You need a huge window.
Yeah, you need a pretty big window, because think about when x is 1. When x is 1, you get 2. Plus 400 divided by 1, you're at 402. So let's set our window, let's go up to 400 and see if that works.
Go up to 1,000. Make it big.
Width will never be negative.
Go big as well.
What's the highest your width could be?
100. I mean, no, 50.
No.
No.
109.
What if my width was 1,000? Could this side be smaller than 1 and still multiply to give you 200?
No, so it has to be less than
Just
2.
ask me some. It could visit me.
It could.
So is there a number you can multiply by 1,000 to get 200?
Oh, yeah.
Yeah, then my width could be 1,000. Could it be 2,000?
So it could pretty much be.
Anything bigger than 0.
Yeah, my width can be as high as I want.
Oh, that's cool.
All right. What's going to happen is your length is going to get
It's
extremely small.
But you're going to have a really.
What would you put in there?
What would you put in it? If the fence is like that big.
Electrons. I don't know.
That's electric.
Microscopic organisms. Microscopic ant farm.
The fence is big.
All right. So x. Let's just go up to I don't know 350. Okay. Y max. Let's go. We said it has to be at least 400. Let's try like 450. Let's see what that looks like. So here's our graph. At 0, we've got a vertical asymptote. So it's going to curve up very sharply. And we're looking for the smallest perimeter. These are all the different perimeters you could have.
So look for the lowest.
Yeah, look for the smallest one. So second calc, what do we use?
Minimum.
Minimum. Pick a point left, right, and the guess. So x is 14.14.
So it will be 56-ish, maybe, I guess.
Okay, the perimeter would be about 56, but the width would be 14.14. How would I get the length? divide 200 by 14.14.
Yeah.
14.14.
It's a square.
So it's a square.
It's a square.
That's not worked out. That's not worked out.
It is.
Yeah, we've done this before. It's just a different way to do the problem involving a asymptote and a minimum. So the dimensions would be a square and the perimeter would be 56. But if you want, you can make the perimeter as big as you want. What's going to happen is the length is just going to start to get, yeah, as the width, yeah, as the width gets bigger and bigger, the length has to get smaller and smaller and smaller.
Yeah, but the perimeter gets bigger and bigger and bigger.
Yeah, the perimeter just grows.
It's more effective than mine.
The perimeter can approach infinity, and yeah.
14 times 14 is 256.
What's that?
Isn't 14 times 14 256?
14. Well, that's the. If you multiply these together, nope, that'll multiply to 200. If you take, if you can get a calculator that works, 14 times 14 will come out to 2. Try 14.14 times 14.14.
It's the perimeter and that side that it up.
Yeah.
199.9396.
199.93.
All right. So the okay, homework tonight. Okay, it's on 235. Okay, try 38 to 43, 45 to 47, and then 51, 52, 55, 62, and 63. We'll go over that tomorrow right away, and then we'll do our test. If anybody needs extra help, I will be after school today.